We start with vectors v1 and v2. v1 equal to 3, 2, v2 equal to negative 1, 4. We sketch these vectors without a lot of explanation. We come over 3 and up 2, and there's v1, and negative 1 and up 4. It's just about here, and here's v2. So here's v1, and here's v2. Okay. So then we ask, where's vector 2v2? What are vectors parallel to v1 along the line of v1, and so forth. So with that sketch to start with, and then we also had a vector v equal to 1, 3. So we could sketch that vector, and the ultimate question that we're aiming at is there a multiple of v1 which, when added to some multiple of v2, gives us the vector v? So the first few questions kind of warm us up for that. First of all, we're asked, where's the vector 2v1? Well, 2v1 is v1 plus v1. To add v1 to v1, we do v1 head to tail with v1, and we have something that looks like this. Here's v1, and here's another v1, so that this blue vector here is 2v1. v1 plus v1, of course, is 2v1. And then we had the vector negative v2. Well, here's v2. Where's negative v2? Well, it's equal and opposite to v2, so it would be in the opposite direction, same magnitude. So if this is v2, this is negative v2. And then we want to add, we want to calculate 2v1 minus v2. So we have 2v1 and we have minus v2. We add them. We put them head to tail. The head of 2v1 becomes the tail of negative v2. And then we add these two vectors. The resultant goes from the initial point of our first vector to the terminal point of our second. And of course, there's a little gap in here. I didn't draw these exactly correctly. But the two arrows would meet at the same point, obviously. Okay, and we know that. So now the question that we really want to look at is there a multiple of v1 that can be added to some other multiple of v2 to get the vector v? Well, yeah, first of all, the multiples of v1, if we look down here, here's the line of v1. Maybe this vector here is v1. Well, this red vector is a multiple of v1, this yellow vector is a multiple of v1, and this purple vector is a multiple of v1. What are these multiples? Well, don't know exactly, but here's v1, here's 2v1. Now, this red vector could be 3v1. Maybe it's 3.2 v1, maybe it's 2.9 v1. If we measured carefully, we could find out. The point is, it could be any multiple of v1, whatever multiple it happens to be. It still has to be along the line of v1, in the direction of v1, so that if its initial point is the origin, it will coincide for a while with v1. It'll go right through v1. Okay? The yellow vector is another multiple of v1. Now, it's shorter than v1. Looks like it's a little longer than half of v1, but maybe it's 0.6 v1, maybe it's 0.7 v1. Okay? If we multiply v1 by a number around 0.6 or 0.7, we're going to get something that looks somewhat like this yellow vector. What about this purple vector? Well, let's say it takes 1, 2, it's probably about, maybe 3/10 as long as v1, but in the opposite direction. So that's a multiple of v1 by maybe negative 0.3. We have to understand this geometrically. Of course, we have to be able to visualize these ratios and these numbers. But we see that any number you multiply by v1 is going to give you a vector along this line. So here's v1. We're trying to get v. How are we going to do that? Well, we have to add some multiple of v2 to v1. When we add two vectors, if we do them head to tail, the head of the second vector will be the same as the head of the v vector. Okay, so the multiple of v2 that we add to v1 is going to be along a line parallel to v2, so it's going to be a vector like this, and our multiple of v1 is going to have to be this. Okay, so there's a way to do this, but that's what it's going to look like. And then we could estimate maybe what these multiples are. Okay, somebody estimated this was half of v1. I said, half would be about there. It's probably more like 4/10. So I said, yeah, let's use 4/10 as the estimate. As it turns out, I should have stayed with half, but that's not what the picture looks like. So according to this picture, this would not be 0.5, it would be 0.4. The picture's not totally accurate, so hand sketch, you know. And then what's this vector? What multiple of v2 would this vector be? Well, it's in the same direction, has to be, and it looks like it's about half. So I estimated C2 would be about 0.5. That is, that if we add C1 V1, where C1 is 0.4, that would be the vector C1 V1. And if C2 is 0.5, this might be the vector C2 V2. And if we add these two vectors, it looks like they add up to V. Okay, so, well, okay, that's fine. That's a geometric picture, and that's not going to give us totally accurate results. Or if it does, it's just dumb luck. So let's see what the actual multiples would be. Because what we're now after is the multiple of V1, which when added to V2 gives us V. Okay, what does that mean? Well, the multiple of V1 is going to be C1 V1, and the multiple of V2 is going to be C2 V2. Okay, and that's what we put together to get V. So our equation is going to be C1 V1 plus C2 V2 equals V. This equation will represent the fact that some multiple of V1 plus some multiple of V2 is equal to the vector V. And we're going to be able to solve that equation rather easily. Okay? Now, there's a little terminology. This C1 V1 plus C2 V2 is called a linear combination of V1 and V2. It's linear because you're just using the first powers of everything. And it's a combination because we're adding the multiples, okay? So a linear combination is a sum of multiples of the vectors that you're combining. Okay, so now we're saying this linear combination, the sum of multiples of V1 and V2 is equal to V. We don't know what C1 is, we don't know what C2 is, but we have a couple of estimates that we think might be rather close. Let's see if our estimates were any good. Okay, how do we solve this equation for C1 and C2? Those are the things we don't know. We don't know what multiple of this one to add to what multiple of that one. Not exactly. Approximately, yeah, these approximations are probably pretty close. How are we going to solve this problem? Well, a lot of people are getting hung up on the first step of solving this, but don't we have the column vector for V1, and don't we have the specific column vector for V2 and the specific column vector for V? We know these three vectors, so let's substitute what we know about these vectors into this equation, and we get C1 times 3, 2 plus C2 times negative 1, 4 equals 1, 3. V1 is 3, 2, so C1 V1 is this, and so forth. Okay. Well, what can we do with that? We've done this. Okay, we've done all these things, but we're putting them together. So that's very familiar. You can multiply this vector by C1. That might be a profitable thing to do. So we go ahead and multiply it. And we multiply this vector by C2, and we get this. I'm not going to read it to you, it's obvious. And then what can we do? Well, we can add two vectors, can't we? So we add these two vectors, and we get 3C1 minus C2 for the first row, and 2C1 plus 4C2 for the second number in the column. Okay? Each number in the column constitutes a whole row because there's only one number in each row. Okay, so anyhow, we have this, and we have this and this. So this has to equal this, which means that, of course, this has to equal this. So 3C1 minus C2 has to equal 1. 2C1 plus 4C2 has to equal 3. Now, that's a system of simultaneous equations. It can be solved on its own. You can solve it by elimination. You could use substitution or whatever. But in this course, we want to go with elimination because it always works for linear equations. So we could solve the system by elimination. What else could we do? Well, we've already seen it. We could write this system as an augmented matrix, and we could reduce that. And actually, I kind of did it off to the side, but as far as solving this problem is concerned, as soon as you have this system of equations, you can regard this problem as solved, provided you know how to solve equations by elimination. Alternatively, we could take this and solve it by writing the augmented matrix, which is actually a little bit easier, and reducing the augmented matrix. If we get an identity over here, then we know what x equals, we know what y equals. Now, not necessarily, we don't necessarily get an identity over here, but unless the multiple of the first equation we add to the second to get a 0 here gives us 2 zeros, we are going to get an identity. Okay, well anyhow, so we regard the problem as solved if we can write down the augmented matrix because we know how to reduce an augmented matrix. Alternatively, one other alternative, we can write this as a matrix equation. Of course, 3 negative 1 times C1, C2, 2, 4 times C1, C2 just gives us this, equals 1, 3. So this is equivalent to this. We didn't even need to write out the system to see what the matrix equation would be. We could go directly from here to here and never have to write out the system and never have to write out an augmented matrix. We can just write out a matrix equation and solve that using the inverse matrix, and here's what our solution would look like. Now, to do that, we have to be able to calculate the inverse matrix. For 2 by 2, that's very easy. For 3 by 3, it's still pretty easy, but it's a little more work. And for bigger matrices, well, it gets to be a lot more work, but it's no harder. Okay, so we can solve this way. So we could solve this, write this as a matrix equation and solve it. We could write it as a system of equations and solve it, or we could write it as a system of equations, then an augmented matrix and solve it. Okay, so the question again is, can we add multiples of C1, of V1 and V2 to get V? The answer is yes. If we reduce this matrix, and I just scratch it down here, you can verify this on your own, we find that C2 is 1/2 and C1 is 1/2. Okay? That means that this estimate was good, and this estimate was close. Of course, whoever said that it should be 1/2 might have been prescient. They might have figured it out already, you know. But 1/2 would have been correct. 0.5 would have been a correct answer. Half of this, half of V1 plus half of V2 does give us V. And you can check that out.